Hey, this is Misty, and this is the test review for momentum and energy, or at least part of it. So this is your review, and we are going to go ahead and work through some of these questions. We will not be working through all of them because you had quite a bit of time to work on them in class. So first thing, it says explain conservation of energy. I'm not going to write that down. You should know that conservation of energy is the law. It states that energy can neither be created nor destroyed, but it can be transformed or changed from one form to another form. So let's look at question number 2. You should have all gotten question 2 done in class, but if for some reason you did not, we will work that together. It asks, the spring constant of a spring is 80 Newton meters, so that's K. If it is compressed 5 meters, that is my distance x, from its resting position, how fast is a 12 kilogram, that's a mass, object moving when the spring is released? So we're going to have to go ahead and use a spring constant. So our formula that uses a spring constant is the elastic potential energy is equal to the spring constant divided by 2 times the distance that the spring is compressed or stretched squared. And that's written at the top of your sheet, although they use a D instead of an X, but we used an X in class when we worked this. So in order to solve for the elastic potential energy, we're going to plug in here, and we're going to have 80 divided by 2, not 20, 2. 80 divided by 2, and we're going to multiply that by 5 squared, and that's going to give us 40 times 25, which if you multiply that out is going to give you 1,000. Okay, so once you have that calculated, we know that that is the total elastic potential energy in our spring. Now what you know is that you have a spring set up and you have like a ball at the end, and it's got all this potential energy here. When you release the spring, the ball will go forward and it will have kinetic energy. What that means is that the total elastic potential energy that is stored in the spring when the ball is released will be converted to kinetic energy, at least in a perfect system. So we're going to set our elastic potential energy to equal our kinetic energy. So we're going to say that that also equals our KE. Now, you know the formula for kinetic energy. That's KE equals 1/2 mass times velocity squared. So using that, we're going to solve for velocity. So we have 1,000 equals mass 12 divided by 2, and that's going to be multiplied by v squared. So we're going to have 1,000 equals 6v squared, and that means v squared is going to equal 167, and when you actually find the square root of that, my velocity equals 12.9 meters per second. So that is that one. Number 3, what force needs to be applied to a 2,500 kilogram car moving at 20 meters per second to stop it if it takes a distance of 30 meters? Now this one's really confusing because you don't have a time and you don't have an acceleration, and you think that you need one in order to use F equals ma. Well, we're not going to use F equals ma. We're going to use a different formula. So what other formula has F in it? And we know that it's this one, work equals force times distance. Do I know the distance? Yes, I do know the distance. Distance is 30. Do I know the work? No, I don't know the work. What I do know is that work is also equal to the change in kinetic energy, which would mean my kinetic energy at the beginning minus, or the end, minus my kinetic energy at the beginning would equal my work. So let's go ahead and look at kinetic energy. Kinetic energy equals 1/2 mass times velocity squared. Do I know the mass? Yes, I do. Do I know the velocity at the beginning and at the end? I do. This is my initial velocity. This is my final velocity. Stopped equals 0. So what I really have here is I'm going to have my final kinetic energy, KE2, is going to equal my mass, 2,500, divided by 2, times 0 squared, which of course just equals 0. And then my initial kinetic energy is going to equal 2,500 divided by 2 times my initial velocity squared, which if you multiply this out is going to give you 500,000 joules, okay? And what that means is that my change in kinetic energy is 500,000, because 500,000 minus 0 or 0 minus 500,000 is going to give you 500,000, just positive or negative, which is just indicating whether or not we've used up or we're gaining. And this is actually being converted to heat as the car stops. So we know that delta KE equals 500,000, and so I'm going to have I'm going to plug that in here. So I'm going to have work equals 500,000. So that's going to mean that 500,000 equals force times distance. Do I know the distance? Yes, I do. Force times 30. And when I divide both sides by 30, I get that the force is equal to 16667. So 16,667 newtons, or 1.67 times 10 to the negative, or times 10 to the fourth. So that's that. How high will a toy car travel up a ramp if it travels at 12.5 meters per second? So let's draw a picture. I've got my car. It's at the bottom of the ramp. It's moving at 12 meters per second. And that's all kinetic energy at the bottom. As it moves up the ramp to a height h, it's going to transfer that energy into potential energy. Okay? So what I'm basically saying is, in a perfect system with no friction, all of my kinetic energy will be transferred to potential energy. So that means that I should be able to find how much energy I have at the beginning and then set that to my energy at the end. So let me show you what I mean. My kinetic energy at the beginning should equal my potential energy at the end. Now the formula for kinetic energy is 1/2 mass times velocity squared. And my formula for potential energy, gravitational potential energy, is mass times gravity times height, correct? Now, if you look at this, my masses, which I don't know, are going to cancel, so I don't have to know them. Do I know the velocity? Yes, I do. It's 12.5. So this is going to be 12.5 squared divided by 2, right? Because that's the same as saying 1/2 divided by, or 1/2 times 12.5 squared, is going to equal 9.8, because that's gravity, times the height. And if you go through and you solve for that, what you will find is that your height is 7.97 meters. Okay? And that is the end of our kinetic energy review. And those were pretty tough questions, but you are going to be asked to do some of those on the test. So let's move on to momentum. These are some pretty easy questions. Just as a review, momentum is a measure of how hard an object's basically going to be hit, like basically the impact on an object. That's a factor of the mass and the velocity. So the more mass or the more velocity, the more momentum. Impulse we define as a change in momentum, but we look at it as a factor of time also. So let's go ahead and let's actually answer number 1. How are impulse and momentum different? So momentum describes inertia in motion, which is basically mass, remember, in our heads. So that's your mass times your velocity. Impulse describes your change in momentum, and that's represented by a force. By a force applied over time, which we represent mathematically as impulse is force times times. So basically, if I wanted to go ahead and talk about how my impulse was related to my change in momentum, I would just say impulse is equal to my change in momentum. So that's that. So we're going to do some practice problems, but first let's go work through question number 2 here and answer all of the parts about elastic and inelastic collisions. Remember, an elastic collision is a collision where the momentum is conserved and it's going to result in objects actually bouncing back. An inelastic collision, a perfectly inelastic collision, is a collision where the momentum is actually going to be, the energy is going to be transferred into heat, and you're going to get a deformation of the object. So like if a car runs into a wall and then just crumples on the wall, that's an inelastic collision. When you had the clay between the cars and they crashed, that was an inelastic collision. So a pool ball strikes another ball and transfers all its momentum to the second ball. The first ball stops and the second ball continues with the velocity of the first. That's perfectly conserved momentum. That is elastic. Okay, an inflated ball bounces up and down, so it is bouncing. That is elastic. A deflated ball hits the ground and stays there. Well, obviously, it's not transferring the energy back up, so that's going to be inelastic. Two atoms collide and bounce in opposite directions. That's exactly the same as the pool balls, so that is going to be elastic. A car sits on a railroad as a train comes and plows into it, dragging it along. That is going to be inelastic. Okay, so now let's do a simple question. What is the impulse of a 300 Newton force acting on a cart for 0.5 seconds? So this is my force, this is my time. My formula is J equals Ft. J is used to represent momentum, and you'll find out why when we get to electricity, because we can't use I. So this is going to be 300 times 0.75, and that is going to equal 225 newtons per second, which is actually going to be your unit there. So I'm going to go ahead and continue on with the rest of the questions on the next video.